All right, and we're live. We are recording. Um, so today we're going to continue our deep dive into Walter Russell's 18 Dimensions of Motion. And today I actually have decided to do the 11th dimension, valence. Valence, you know, it as Russell says, is one of the great dimensions, by means of which states of motion can be measured in their relative tonal pressure intensities. The term valence is a standard unit um, of tonal relations, just as a day is a standard unit of rotation, or a year is a standard unit of the periods of revolution, like the Earth around the sun. And, yeah, valence is used in chemistry. And it's the way to kind of understand how one element will bond with another element, or how one compound will bond with another compound. And so I'm going to share my screen, because of course we've got to do some diagrams. So in terms of how valence is connected to kind of all the other 18 dimensions, because as we've said before, every dimension is related to every other of 17 dimensions of motion in Russell's concept. And valence is talking about, I should bring up, sorry, one more picture. We've seen this before. This is our periodic table, right? And as we zoom in kind of to our favorite octave here, the carbon octave, we're going to, now I'm going to show you this. And what we have here are essentially, you see there's like a sun here. We see our formula of the lock potentials with, the plane of +1, this plane of +2, +3, and then the 4 plus, where he's showing a sun. This is, you'll notice, a spiral spiraling up towards the 4 position on this side, and another spiral spiraling up to the 4 on this side. And this would be the equator right in the middle, the equator of the sun. So, and as we talked about before, these two spirals would be in two cubic wave fields, adjacent, two cubic wave fields that are adjacent to each other. And so this would be like at the corner of one of those wave fields where that sun is. You'll see he's got one side labeled as mother and the other side labeled as father. Now, this is a black and white picture, but we know that from when we did the dimension of color, we know that one side, which is the red side, and the other side is the green side or the blue side, depending on what book you're reading from Russell. So one side would be the mother side, and one side would be the father side. In this case, the red side is the father side or male side, and the blue side is the female side, or mother side. So now valence, in terms of traditional science, is related to the traditional periodic table. And so just like one example, we probably use this example all the time, but when we look at two elements, in traditional science, atoms of elements are made up of materials that are said to have charges. Okay. And so, for example, in traditional science, we're going to look at the chlorine right here, which would be -1. And on the other side, you'd have sodium, which would be a +1. And this is definitely, you know, the difference between traditional science and Walter Russell's concept is that traditional science believes that there are particles like electrons that have a single charge. And in the case of the electron, it's a negative charge. So traditional science tells us all electrons are negatively charged. And all protons, which is another particle, are positively charged. Now, Walter Russell's concept is quite different. Walter explains to us that there are actually only two forces, and that those forces cause spirals, either centripetal, gravitative spirals, or radiative, expansive spirals. Sorry, what's the centrifugal spirals? Now, and Russell says that all matter, whether it's a sun, galaxy, or a planet or a particle, they are doubly charged with positive and negative. Now, when I say that, it doesn't mean the same thing as the traditional science positive and negative charges. What Walter Russell is talking about is, in his concept, the positive charge would be the male centripetal spiral, charging up to be over unity of equilibrium. So he calls that positive. And the opposite of that would be the radiative spiral, centrifugal spiral, being, minus equilibrium. He calls that minus because it's discharging. So it's either charging up, he calls plus, or discharging, he calls minus. Charging up, he calls male, and discharging, he calls female. Charging up, he calls, positive. Discharging, he calls negative. So the formula of the locked potentials that we have, as we all know, they correspond to these planes of locked potential positions. He says that at these planes of locked potential positions, that is where we will find what traditional science calls elements of matter. So when we look, well, one more time for the audience at home, we're looking here at two spirals, one spiraling up this way and the other spiraling up this way and meeting at the 4-4 position. And we're going to take it to the periodic table. Silicon is at the 4-4 position. So now, once again, we're looking at, one spiral going this way, coming to silicon, and another one going this way, and they're meeting here at silicon. So when Walter Russell talks about, the 11th dimension of valence, he is talking about, say, sodium. What is the valency of sodium? Well, it corresponds to the +1 position of the locked potential positions in the formula of the locked potentials. And chlorine corresponds to the -1 locked potential position. So when these two elements, chlorine and sodium, meet together, they are a +1 and a -1. So therefore, they are a perfect mate. And Walter actually described this, let's see, you see neon right here as an inert gas. And then we see argon here Okay. And so we're going to talk about this area from argon over to neon. All right. This little rainbow over here of these colors. It's one spiral here. This would be the corner of the cube at silicon. There's another spiral here. And he says that essentially it's seven tones, let me hold on one second. One, two, three. He's essentially saying that sodium at +1 and chlorine at -1, they are a pair. They're a perfect mate pair. So that's one pair. Then you've got magnesium at +2 and sulfur at -2. That's a second pair. Aluminum at +3 and phosphorus at -3 would be a third pair. And then silicon is actually another pair, but it is essentially one half is on this side and the other half is on this side. And there's an equator here. Like this is a sun and there's an equator. And so essentially it's like a pair. So it's like four pairs. And he says it's seven tones because each one would be a tone. Sodium would be a tone. Chlorine would be a tone. So we got 1, 2, 3, 4, 5, 6. And then he calls this tone a 7. It's like a doubly sexed tone. You know, each element is a tone, as we talked about in our dimension of tone or sound, because they each have their own frequency. Okay, so so in terms of valency, in Russell's concept, it's really about the locked potential position. So +1 would go with -1. All right, so now let's move on to another slide here. Okay, so this is Russell's explanatory chart number 1. And he really is starting to get into chemistry, you know, which is appropriate. If we're going to be talking about valence, we're going to kind of talk about chemistry a little bit and how the elements come together. So what we're seeing here, all of these little circles with letters in them, these are all the abbreviations of the elements. Like O is oxygen. Okay. Let's see. Cl is chlorine and Na is sodium. And so he's saying this chart is indicating the tonal mates of maximum stability. Walter talks about in this universe of motion that it's a temporary, you know, fleeting universe. You know, even when something is like hard as steel, it's still in motion and it's still temporary. I mean, temporary can mean, you know, thousands and billions of years, but, you know, it is in motion and it has its life cycle from birth to maturity, then back to death and repeat. So he's saying that when there is motion, there are various levels of stability of that motion. And, you know, he talks about the two universes that we've talked about before. One is the three-dimensional universe of all this motion that we see, and he calls that the fleeting, temporary illusion universe. And then we have that other universe where there's no motion, you know, the still light of, you know, he called it the magnetic light or the white light, you know, of God or of the God mind. And that, he says, is the real universe. So when he talks about stability, he actually says that motion will be spinning like a top, kind of. And the faster it spins, if anyone has ever seen a top, if it's spinning slowly, it's very unstable. It's wobbly. But if the faster it spins, it comes up and then it will like stand up. And so the illusion of stability will be there, the faster that it spins. And when it's at that maximum position of the 4 plus, it'll be 90 degrees up and like maximum illusion of stability. So what he's showing here, um, let's see what he says here. Stability or instability is the relative willingness of elements in union as compounds to come into association with each other and their relative power of holding themselves together in combination when so joined. So, every combination shown in this diagram represents maximum stability. And so, let's see, let me put up the periodic table over here, one also. See if we can find let's see, if we kind of memorize this, let's see, sodium, magnesium, aluminum on that side. The other side is chlorine, sulfur, and phosphorus. So let's see if we can find that over here. Um, let's see, there's chlorine, phosphorus. Let's see on this side, there's sodium, lithium. Okay. Wait, this is how it's, okay. Sorry. This is the way this is organized. These down here are in the +1 or -1 position. The next level up is the +2 or -2 position. Up here, you got the +3 or -3 position. And then all the way up here, you got the +4, -4 position. These here are as we get to the higher octaves, there are those elements that are in between
The
position
isotopes.
three and position 3 and 4. Exactly. The isotopes. Thank you, Scott. Okay. So if this is the first position, that's why we have sodium right here and chlorine right here. And this is going up octaves. Like this is the lower octave, like hydrogen goes up an octave, so it's like octave 1, 2, 3, 4, 5, 6, going out like that. So we see that the +1 and the -1s, they bond together in whatever octave. So the chlorine and sodium are in the fifth and sixth octave. But then you go up to the seventh octave, seventh and eighth octave. That's when you'll have, let me make sure I'm telling you the right thing. Hold on. I am cheating and looking at the periodic table over here on this other screen. So we're going to look at, say, Br, I think is bromine and potassium. Right. Potassium is in the sixth octave and bromine is in the seventh octave. And then the next would be iodine, which is I. And what is that? RB, I think is rubidium. Right. Rubidium is in the seventh octave, and then iodine is in the eighth octave. So rubidium here, seventh octave, iodine here, eighth octave. So just so you see how this chart is structured, it's the lower octaves here, and it goes to higher octaves as it goes out towards the outside. Now, this is at potential position 1. Let's go to potential position number 2. So what that would look like on our periodic table. Let's see, where's our good old. So we did sodium and chlorine, which we all know is table salt. So next up would be sulfur at position -2 and magnesium at position +2. They are the true mates. So here we are. Let's find here S, there's sulfur. And you see it's matched with magnesium, the true mates of each other. So, and this would be position 3. So hopefully you guys are seeing the pattern here. You got position 1, position 2, lock position 3, and then 4, 4. And so that's how the true mates are in the most stable positions. He's got these arrows, pointing to which ones are the most stable. If those two mates come together, there's no other element that could separate those mates apart. They're only going to get separated if they get heated up, in a high enough temperature to literally like melt them away from each other. Okay.
Can I ask a quick question while we're on this page?
Yeah, sure.
So he's got these little symbols either side of this chart. It looks like they are representing the four locked potentials, and they're kind of all mirror images of each other except the bottom two there. Do we know why he's got the bottom two symbols not mirror imaged and all
That
the
is
others are?
right. That is a great question. And that also is a question I have. And I've always, when reading this book, I notice he has those throughout the book. This is in the Universal One. He's got them kind of throughout the book. And I think he was kind of experimenting with this kind of notation. And I noticed it, but I never went deep enough into to try to figure out exactly what it was. Because that notation is on many of his diagrams. And I'm sure if we kind of like studied it, we could probably figure out what it is. But yeah, I don't have the answer of why those two are not mirror images of each other. You know, it could be a mistake because, like, you look here and over here, this symbol is the same as this symbol. Maybe this was supposed to be up here on the top to be like a mirror image that way. So I'm not sure. But that is actually something I'm also curious about. We could maybe explore that another time. Let's see here.
Also, to me,
Yeah.
I think that it'd been easier to understand this a little bit if those symbols on the left hand and right hand side were just up a little bit higher.
Oh, right. Right. Yeah,
Just
because like
because it's confusing when you have two on the left and two on the right, but that's really the one
right.
balance.
Interesting. Yeah, it seems like this would be the 4-4 position. This would probably be the 3. This would be the 2.
Three and the
then,
four are okay. The two and the one, I think, are out of position
right.
just a
Right.
little bit. The three
Right.
needs to be up a little bit too. So one, two,
Yeah.
and three need to be up a little bit higher. That's all.
Yeah, I would agree with that. Yep. Yep. Um,
Four could technically be there once at the very top.
right.
It is.
Yeah, exactly.
Mm.
Okay, so let's see. Right. Every combination shown in this diagram represents maximum stability. Each unit is the tonal mate of the other. Together, they represent one action and reaction of the universal constant. They combine into equal quantities. Each is the opposite of the other, and in combination, they neutralize their opposition in unity. He says, note the true tonal mate of hydrogen is not fluorine, it is helionon, an undiscovered tone in the fourth octave. He says, examples of stability and union. All of these pairs are in the same pressure zones and same orbits. Now, that pressure zone is what we're talking about, the pressure zone of +1 and -1. Then the pressure zone of +2, -2. Pressure zone of +3, -3. And finally, a pressure zone of +4, 4. Let's see here. Right, same pressure zones and same orbits. The less active solids may enjoy separate existence, but as they increase in activity, it becomes increasingly difficult for them to exist separately in free state. We're going to go to explanatory chart number 2. Now, this one is really, oh man, when I first read this, to me, this is like literally Russell's chemistry. This is really showing how we can understand chemistry and how things come together. And this right here, in my opinion, is what current chemistry is missing. Like they don't quite know this. I mean, they kind of do know this just from like a lot of trial and error. Like traditional science knows a lot about all of the elements, and many chemists have done many trial and error, experiments. And so they do know like a lot of this and how all these things go together, but not in the way Russell does here. Like Russell is giving like rules so you know how everything comes together. Whereas chemistry they were just kind of experimenting and seeing what makes what and that kind of thing. Okay.
And this is the roadmap to know exactly what goes with what.
Exactly. Right. This is the roadmap. So we have our same, it's the same kind of setup as the previous diagram we were looking at the previous chart, but now he's going to go into some kind of specific examples. So we'll start at A1. So he's got the letter A over here and the number 1, and that is pointing to chlorine. So he's saying, look, sodium and chlorine, NaCl, will come together with explosive violence at ordinary temperatures because they are exact tonal mates. They are of opposite sexes, and their orbits are in same low pressure zone where integration is more easily affected. Let's see. So we've got chlorine here, and he's got a line from this number 1 going all the way through, pointing over to sodium. Sorry, it might be hard to see that, but that is Na, sodium right here. And he's got all these lines pointing to sodium because we're going to be comparing to sodium. So he starts with chlorine as number 1. So chlorine and sodium, perfect mates. Now, he says the degree of willingness of this series, known as the halogens, to combine with sodium, which is Na, is in the order indicated by the numbers. So number 1 would be chlorine, because that'd be a perfect 1-to-1 match. But what's number 2? Number 2 would be fluorine. Now remember, each line here going up and down here, that is a different octave. We're going to the lower octaves on the inside and towards the higher octaves on the outside. So fluorine is in a lower octave than chlorine. So that is the number 2. It will match up with sodium. It won't match as perfect as number 1, but it's the next one that'll match up in the order of willingness. Now, if you go to a higher octave, so we're going this way, you got bromine here. That's number 3. It will match with sodium as number 3, the willingness. Then you've got iodine. You're going up another octave to iodine. It's going to be less willing to match with chlorine. I'm sorry, sodium. And finally, all the way out to the highest octave. He doesn't even know what this is, but that would match. That would definitely not want to match with sodium. Now, so what we've learned here is that the lower octaves, which are in lower potential, they will match up easier than a low potential thing matching up with a higher octave or higher potential mated pair. And when I say mated pair, I mean, remember, sodium, let's look at our periodic table 1 second here. Sodium, remember, is in the +1 position. So essentially what we're looking at in terms of, mates, we want to look at the -1 position. So we look at chlorine, that's -1, and it's the perfect mate. But now we're going to go up an octave, like over here to bromine. That's also -1. Oh, sorry. No, right. That's also -1, but it's in a higher octave. So it's -1, and sodium is +1, so they'll still get together. So, you know, um, but just not as willingly. And then if you keep going up higher to say iodine, well, iodine is also a -1, but it's even higher octave, so it's even less willing to match. And that's what we did here. We went to bromine, then we went to iodine. So those are all +1, and all of these are -1. So that's kind of, the difference there. Now we're going to take another example. So the first example, he was doing +1 and -1, let's see, and changing the octave. Now this time we're going to change the pressure zone. So we look at B. Here's B. So we're going to be looking at these lines here. Okay. So nitrogen, when unwillingly united with any of the halogen series, will break away with explosive violence, the intensity of which decreases in the order indicated by the numbers. So let's see. Nitrogen is up here. Let's look on the periodic table. I like to look on the periodic table just so I know kind of what we're talking about here. Nitrogen would be in the 3rd pressure zone. So that's a -3. Okay. Here is nitrogen right here, the green at -3. Oh, we got 1 minute. Okay. Thank you, Scott. All right. So I'm going to shut it down, and then we'll start this whole nitrogen comparing thing. And I will see you on the next video. Okay, so we're starting the recording now. So, okay, so we're going to be talking about nitrogen as the example. So we see nitrogen is in the -3 position. It's in the 3rd pressure zone, 1, 2, 3. So if it's -3, then its true mate would be boron, +3. Okay, which is right in the same, the same octave, or in this case, adjacent octaves, 4 and 5. But, they're the closest octave. This is the closest mate in terms of octave and in terms of pressure zone, 3. Okay, so, and I think what we're going to be doing is comparing, right, we're going to start comparing, let me go back. Well, just so I see, fluorine, chlorine, bromine, and iodine. Let's see. So that would be fluorine. Oh, I see. Okay. All right, I have to bring back the other. Okay. So we've got nitrogen. So nitrogen is in the 3rd pressure zone, as we said. And on this diagram, its pressure zone is down here, number 1. Pressure zone 2 is here, and pressure zone 3 is up here. So nitrogen, being -3, will unwillingly unite with any of the halogen series, and it will break away with explosive violence, the intensity of which decreases in the order indicated by the numbers. Fluorine is -1. Okay. And nitrogen is -3. Okay, so already we're in the same sex, both negative. And we're trying to combine a negative of the 3rd pressure zone, a -3, with a -1 of fluorine. Then next would be chlorine, which would be an octave higher. Therefore, it'd be higher potential, still negative. Then bromine, because remember, we're going up the octaves as we go out. These lines that are up and down, when we go out this way, the octave gets higher. Till finally, iodine, which is, even higher octave. And so what is specific there is that when something is in an octave that's kind of close to, like octave 4 and octave 5, they're closer. But if you go, say, octave 4 and octave 7, well, 7 is a farther away octave, so it's not going to combine as easily. And if you do octave 4 and octave 9, then that's even farther away. And so they're really not going to, they're definitely not going to combine. They are not want to get together. Okay. Now, the last example looks like we're going to be talking about lithium. We're going to be doing this example of D1, D2, and D3, these over here. So let's see. We're going to start with lithium. Lithium is in the +1 potential position, or +1 pressure zone. It's on the positive side, and it's in octave 4. Okay? So we're going to be comparing it to some other elements. Let's see, what are we going to compare it to? Lithium and fluorine will come together as lithium fluoride with Valence. So let's see. We've got lithium here, and it looks like straight across is fluoride. So I'm guessing that is the true mate. We'll just confirm that. We got lithium as +1, fluorine -1. Yep. And they are right next to each other in terms of octaves, octave 4 and octave 5. So that's the true mate. Going to come together with explosive violence. Next. Right, they'll come together and make lithium fluoride with Valence. While D2 and D3 combine with increasing unwillingness because of the increasing pressures and other dimensions of their tonal positions. So if we look at D2, now we're comparing fluorine and what's that? Beryllium, I think is Be. So let's just take a look. Looks like we went up a level. All right, let's take a look on our periodic table. We're doing fluorine and beryllium, right? Where's fluorine? All right, so fluorine is -1, and beryllium is positive, but it's +2. It's in a higher pressure zone, second pressure zone, where fluorine is the first pressure zone. Let's see, and then we're probably going to do boron, which would be the third pressure zone, but let's go back and see. So, right, fluorine and beryllium. And now we're doing fluorine to D3, yep, to boron. So that's just showing that you can have the correct sex, where one is negative on this side and the other mate is positive on this side. But if you go up a pressure zone, it will not want to get together as much as when it's in the same pressure zone as pressure zone 1. And then you go up one more pressure zone from 2 up to +3. Well, it's still the correct sex. You got one is negative and one is positive, but the pressure zones are farther off. One is +1 pressure zone. The other one is +3 pressure zone. I'm sorry. Well, I shouldn't have said positive. Just the pressure zone consists of the -1 and the +1. That is pressure zone 1. Pressure zone 2 is the -2 and the +2. Pressure zone 2 and pressure zone 3 is the -3 and the +3. And then the 4++ is the pressure zone 4. Okay. So what Walter is showing here, and it's hard to get this all in the first just reading, but you can go back and watch this. He's just showing you the different ways how elements will come together and the willingness that they'll come together. So number one, sex is one of the dimensions. If it's positive on one side and negative on the other side, then they're going to be good mates. They're going to be better mates than if both of them are the same sex and are both negative. Okay. Then they're going to be better mates if they're in the same pressure zone. Like a +1 and a -1 will go together. A +2 and a -2 will go together, right? A +3 and a -3 will go together. But the farther they are apart in pressure, the less they're going to want to go together. So if you got a +1 and a -2, sorry, like a -1 and a +2, will kind of go together, but a -1 and a +3 will go together even less. So that's pressure. And then he also showed us how octave makes a difference. And he even did it with um, positive. He got the correct sex. He got a negative, say, fluorine, or sorry, no, we did sodium. We did positive sodium going with negative chlorine, and that of the same, close octave, but then a positive sodium and a negative bromine. Bromine is a higher octave. So the farther the octave gets away, the less they're going to want to go together. Um, and then the last one he did was even if the sex is wrong, they can still try to get together, but going farther apart in octave will make them want to go farther apart. And he described that as they will break away with explosive violence, and that's because they're the same sex, so they're going to repel each other. But they're going to repel each other even more when they're the same sex and they're even farther apart in octave. But the way nature works, you can always kind of get things together if they are heated up high enough and intensity enough. It's like the melting pot. It's like when you melt metals. It's like these two metals won't go together, but if you heat them up enough, they become molten and you can mix them together. You like literally you can stir them together, right? And then like let them cool and they'll form. But it's only going to be that way if you superheat them up, otherwise they're going to like repel. Like if we're talking about at room temperature, no, they're not going to get together. They're going to repel. So these are the various ways. So we have sex is one dimension to look at. We have pressure is another to look at, like pressure zone or, 1, 2, or 3 or 4. And then we have octave, in the periodic tables of in the octaves. Oh, forgot my video. So he's given us rules of how matter comes together and what makes it more stable versus unstable. You could have a semi-stable, negative fluorine and a positive beryllium, but if lithium comes in, which is on the same pressure zone, it's going to kick beryllium right out, and it's like this is my true mate. And nothing can stop us from being together. They're going to neutralize each other. We have one more chart. I think here. Well, actually, we have two more charts. So we're still talking about valence. Okay. And oh my gosh, that's right. I'm sorry, guys. This is this is like totally like chemistry. We are literally doing chemistry. We are learning chemistry in Walter Russell's concept. And chemistry is not an easy subject just in traditional science. So, and it's in depth, let's see here. This is indicating the tonal mismating in variable instability. Now, what does that mean? Let's see. So we're going to continue here with number C, hydrogen, right here, and fluorine over here, being almost mates and in nearly the same pressure zone, same plane and same orbit, will unite part for part. So meaning like this same amount of hydrogen will match with this same amount of fluorine. Now, oxygen, which is oxygen. Oh, where is oxygen? Oh, is right up here. Or beryllium, which is Be, right up here. See, we see those are in the second potential position or pressure zone. So oxygen or beryllium being one pressure zone removed and consequently of double potential will require 2 parts of hydrogen to their 1 they're one part, and then only unite under pressure of higher temperature. So what he's saying here is oxygen, if we look at hydrogen and oxygen, since oxygen is one pressure zone up, has twice as much potential, one oxygen is going to require 2 parts hydrogen. And so what do we got? We got H2O, right? 2 hydrogens and 1 oxygen. And that's water. And if we have hydrogen matching with nitrogen, I'm sorry, I skipped ahead. We did hydrogen and oxygen, which is D, which is D also. You would still need 2 parts hydrogen to 1 part beryllium. Now we look at E. Nitrogen or boron, so we have nitrogen up here on the E line and boron right here on this E line. They are 2 pressure zones removed from hydrogen and require 3 parts of hydrogen, and they require higher pressures to melt them together, to get them together. And it says the same rule of sex applies. Last but not least, carbon, 3 pressure zones removed and 4 times higher potential, demands 4 parts of hydrogen to remain in union with its 1 part of carbon. And also the high temperature pressure of the electric arc, that's a torch, right, is needed to induce the union of hydrogen and carbon. So you need 4 carbons because 1, 2, 3, 4 pressure zones away. So that's just an example. And I'm looking at, I remember when I first read this, I was like, oh my God, this is like so brilliant how it kind of all comes together. I mean, when we were studying all these different dimensions, they all come together to create this chemistry. And it's like the reason why, water is H2O. Okay. We're going to go to the last chart here. And this is order of hardness and compactness. Now, hardness means degree of solidity or resistance to penetration. Hardness is the result of opposition to inertness. Therefore, the farther an element is removed from the inert gas of its octave, the harder it is. Let's see. It says, so once again, we have these are all our elements. Still the same format where like the lower octaves are on the inside here. And as we go out it gets to the higher octaves. And so the inner arrows indicate the direction of increasing hardness, which means, let's see here. Ooh, let's see. I think he's saying, yeah, these are the inner arrows, and they're going up towards this way, increasing hardness. Because see, what do we have here? We have carbon. So remember, this is the lower pressure zones down here, position 1. As we go up to the next pressure zone, which is, the +2 and -2, these elements are going to be harder. We go up to the +3 and -3, these elements are going to be harder. And even through the isotopes, they're going to be harder and harder as they approach the 4++ position. These elements at the 4++ position are the hardest elements. They're the most solid or resist penetration, most dense and compact. The periodicity of hardness is in the order of the pressure zones. Those of the first pressure zone being the softest, pressure zone 1, -1 and, the potential positions of -1 and +1. And the pressure zone of the fourth being the hardest, the 4++. As the elements harden, their ecliptic areas contract from maximum expansion and minimum extension in the first pressure zone. Okay, we haven't learned about the ecliptic. So actually, I don't even want to, that's not going to make any sense to anybody at this point. Once we do ecliptic, then I'll come back to this because it'll make sense to you guys. Once we learn about ecliptic and ecliptic expansion, then we'll come back to this and I'll read it here now and we'll read it again later. But basically it says, as the elements harden, their ecliptic areas contract from maximum expansion and minimum extension in the first pressure zone to zero expansion and maximum extension on the carbon line of the fourth pressure zone. So what we have just done, we've gone through valence, and we've seen now some rules of chemistry. We've seen the rules of valence that will tell us how elements will come together or how they'll be repelled. And it also shows us like the reason why, like how much will they, like in what magnitude will they be attracted or repelled? The like mates are going to be attracted much greater than the mates that are not of the same pressure zone or not of the same octave. There is a couple more things worth talking about. Oh gosh, yeah, we only have 4 minutes and 47 seconds. I can get through this because we are almost done here. Let's see. He says, it will be observed that the valency of all of the elements is in accordance with the formula of the locked potentials. The inert gases have zero valency, for they will not unite with any other element, although they will unite very readily with each other, not as compounds, but as interlocking substances. The inert gases of lower potentials integrate within the inert gases of higher potentials. One other thing, and let me put the periodic table back up on here. He says, in adopting standard units of valency measurements, the physicists have based their calculations from the element hydrogen as the unit of one, because traditional science knows as hydrogen as the first element. So they kind of base the whole periodic table off of that one element as unit of one. Russell says this is akin to adopting one note on the keyboard of a piano as a key tone for every octave scale, whether it is for the key of 1 flat, 3 flats, or 5 sharps. As in musical tones, each octave has its key note, which is a definite tonal relation to the entire octave. So in chemistry, each octave of the elements has its own key note. So hydrogen, which would be here in like the 4th octave, should be adopted as the unit of valency measurement of the 4th octave only. Lithium would be 501. And so that should be the keynote for the 5th octave. And then 601 would be sodium right here. Boom. That should be the keynote for just this 6th octave here. And finally, it keeps going up, potassium 701 right here would be the keynote for this octave. Rubidium would be 801, the keynote for this octave. And so on. So, and he says, so when the standard units of valency measurements are changed to conform with true tonal relations, valency can be more accurately calculated. But while one element is forced to stand as a unit constant or keynote for all of the tones of every octave, the miscalculations of valency will be as disproportionate as similar tonal calculations on a keyboard would be inharmonious. And, that's just Russell back in 1926, like telling them, like, guys, you got the periodic table wrong. You're basing, everything on hydrogen when no, it's really, you should be doing it octave by octave. So that blew my mind the first time I heard that. And I don't know chemistry well enough to explain that exactly. And if we had a scientist who understood the concept of valency measurement based on hydrogen, we could tell them, hey, what if you based your valency measurement on, the keynote of each octave? And so that's kind of one of the things I'd like to talk to a chemist about. But so anyway, that is the concept of valence. It is definitely based on the locked potential positions, the formula of the locked potentials, and it shows how elements can come together. And as we went through the whole in-depth thing, it is also determined by other dimensions. There's the dimension of pressure zone, 1, 2, 3, and 4. But then there's also the dimension of sex, where the plus and minus will be attracted, the minus will repel, and the plus will repel. And then there's also the octaves, going up higher and getting higher potential. The farther away you get in potential, the less likely the elements are going to come together and stay together. And the higher potential or higher pressure requires a higher temperature to like melt it to force them to come together. As we've now gone through everything. And so I hope you guys can see how valence, which is the 11th dimension, how it is connected with all of the other dimensions that we've studied so far. And, next week we'll move on to the next one. But that's pretty much it for today. That was really one of my favorite, like the chemistry, Walter Russell's chemistry is one of my favorite things because I feel like that's something that directly can be measured. Like traditional science know about all these elements. And so this is where we can say, all right, well, is Walter Russell's concept correct? Does it match nature? Like, it's pretty, I think it's pretty awesome because like I could look at, like, here's an example. We'll do one quick example here. I can look at this periodic table and I'm not a chemist. I don't know. However, I know Walter's concept. And so I know that fluorine, which is right here, which is -1, fluorine should combine with, I don't know, potassium, which is +1. And they're both in the first pressure zone. So, fluorine potassium would be a combination of something. Now, we could check this here. Let's just for laughs. Let's see if fluorine potassium is a combination. I'm just gonna search it. We'll see. Or maybe it's potassium fluorine. Maybe I don't know. Fluorine. I don't know if I spelled that right. Let's see. There it is. Boom. Potassium fluoride. Wait, is that what it said? There it is. Potassium fluoride is the chemical compound with the formula KF. And look at that. We know that potassium and fluorine, since we are looking at our Walter Russell periodic table, since they're both in the first pressure zone, they should match up 1 for 1. So the formula should be KF, 1 potassium and 1 fluorine. And we could try it again and say, well, if lithium is +1, what if we match it with a -2? It's a random -2 one. Selenium. Let's try potassium and selenium. So it should be selenium should require 2 potassiums to match. So let's try it. Selenium and potassium. I mean, I don't know. I didn't plan this ahead of time, guys. I don't know what selenium potassium is. I don't know if it's a. Okay, here we go. Potassium selenide. Is it there? Let's see. Does it say what the formula is? Let's see. Yep, there it is. K2Se. That means 2 potassiums and 1 selenium. Boom.
And
Walter,
you never see that on a normal chart, a normal periodic table, because they have it all messed up.
Right. That's the other thing. Yeah. Now, because I do want to do still like a thing on chemistry, which is like, I mean, it's in depth because it's chemistry. But right, that would be something like, when I do that kind of video, I want to show side by side Walter's periodic table and the Mendeleev periodic table and like how things match up and don't match up. But just like there, just because we know Walter's concept, I knew that there'd be two potassiums and one selenium. Like, like, it's amazing, and I could just see that in the periodic table. So I hope that is a nice example, or that's just like, it was a nice little proof of Walter's concept right there. I hope you guys enjoyed. I hope it made sense, and we'll continue next week. It looks like we got about a minute left, so if there are any comments or anything, let's see. Olivia, my favorite after dinner mint. So, okay, guys. Well, then I guess I'll close the meeting out. Okay. Bye, guys. It's great to see you guys again. I'll see you next time.